Today our topic of discussion is well-formed formula. But whenever we read anything, first we have to understand what is the purpose, means why we are learning this well-formed formula. See, the answer is we need well-formed formula based representation for knowledge representation in AI. Now, what is this well-formed formula? So I have discussed about propositional logic. So what I have discussed, see, propositional logic uses symbolic language to represent some logical structure. So here my point is, this propositional logic, we can say that it is a kind of symbolic language which is used to represent some logical structure. So like any language, this symbolic language has some rules, means we have to use that rules in order to put some symbols together in the right way so that we can create one proper logical structure, right? So for representing any symbolic language, rules are very much important. So we have already discussed what are the different rules we have to follow in order to represent propositional logic. Now, here the question is how well-formed formula is connected to it. See, whenever we are talking about propositional logic, basically we are talking about symbolic language. And whenever I'm talking about symbolic language representation, we need some syntactic rules. So, whenever some specific syntactic rules are used in order to represent some propositional logic, it is called WFF. So, what is WFF? See, it is not a new entity. So whenever we are applying some specific syntactic rules in order to create some symbolic representation so that we could represent some logical structure, it is known as WFF. So what we are going to study today? So today we are going to learn some specific rules by which we will be able to define WFF. So what is WFF? It is not a definition. So whenever we will learn some rules, together all those rules will help us to create WFF. So that's why today we are going to discuss which symbolic representations are known as WFF and why, and which symbolic representations are not considered as WFF and why. So this thing we have to keep in mind, because if all propositional logics are WFF, then we can say that why we are learning extra rule for learning WFF, right? So it means we have some specific rules in order to represent WFF. So let's see what we can define. See, first we will learn what rules or what representations are considered to be WFF. Now first, see, the syntax of propositional logic are easy to learn. We have already discussed this thing. And this syntax of propositional logic uses three rules. First, any capital letter by itself is a WFF. Now, first rule. So whenever we are using any capital letter, say A, it is itself known as well-formed formula. So what is the meaning of this rule? See, whenever I am using any capital letter, it means I am going to represent some constant. Constant means, say, place name or name of a person, or I'm specifying some color. So whenever we are going to represent some constants, we will use capital letters in order to represent them. So whenever we are using any capital letter, it means it is already in WFF. This is rule number one. Now rule number two. Any WFF can be prefixed with not. then it is also a WFF. Means, see, A is a constant, it is a WFF. Now, what is rule number 2? According to rule number 2, if A is a WFF and it is prefixed with not, means we are writing not A, where A is a WFF, then not A is also termed as WFF. So any WFF prefixed with not is also termed as WFF. This is your rule number 2. Now rule number 3. Consider we have two WFFs. Two WFF means, say A is a WFF, well-formed formula, and B is also a WFF. Now, according to rule number 3, if we can put together this two WFFs with some connectives like A or B. So this is a connective. So whenever we are using connectives in between two WFFs, then the overall representation enclosed in a parenthesis like this, round parenthesis, is also considered as WFF. So this is rule number 3. And what kind of connectives we can use? We can use dot connectives, we can use or connective, we can use subset connectives, equivalent connective, any connectives. So whenever you have two WFF and you are placing connectives in between these two WFF, then the overall representation is also considered as WFF. Now I will explain these rules in more details with some good example. Before that, we have to understand one more point. That is, which representations are not considered as WFF. This thing you have to keep in mind. Say, I am just writing that A not. So whenever the not symbol is placed after any variable or constant, this kind of representation, it is not considered as WFF. This is the first point. So not must be a prefix of a constant. Then it will be a WFF. Then rule number 2, which is not a WFF. See, whenever we are writing parentheses like this, see A and parenthesis. So we are representing a single constant and then we have parenthesis over here. So parentheses are only introduced when joining two WFFs. Means if you are using parentheses for representing a single WFF, then this is not considered as WFF. However, whenever you are using parentheses in order to connect two WFFs, then it is a WFF representation. So parentheses with single WFF is not a WFF representation. So these are some kind of representation you have to keep in mind. Now what is the third rule? Now I have considered that whenever A is a WFF and B is also a WFF, and whenever you are using connectives like this in between them, so it is a WFF representation. However, if you write A and then connective, so this kind of representation enclosed by parenthesis, it is not a WFF. So whenever we have this kind of representation A dot B, since we are connecting two WFFs with connectives, then it is a WFF. But single WFF and we have one connective symbol immediately after it enclosed by parenthesis, it is not a WFF. So these rules you have to keep in mind. So these representations are considered as WFF and these representations are not considered as WFF. Now I am going to give you more details about these three rules and I will try to define this rule in a more specific manner with some specific example. Then only you can understand which representations are actually considered as WFF. Now let's start with the concept. See, rules of constructing WFF. So we are learning this one. Whenever you have some representation like this, that is the capital of India is Delhi. So this is the representation. Now my question is it a WFF? Now we have to think it comes under which rule and how we can prove that whether it is a WFF or not. See, whenever I am talking about this kind of example, we can say that it is a specific proposition. So what do you mean by specific proposition? See, this statement or representation is having its true or false answer. Means it's a declarative in nature. So whenever any given example is declarative in nature, that is, it is having its truth value, it is known as specific proposition. And it is dealing with some constants. India, Delhi. So at this point of time, it is known as WFF. Now you can ask me one question, that is, it comes under which rule that we have discussed. So basically the rule is, you have to keep in mind each propositional constant which is also known as specific proposition are known as WFF, right? So this is the first example of WFF. So whenever you are dealing with some proposition, which is a specific proposition, means it is dealing with some constants, it means it is a WFF. Now consider the second example. See, the example is written as X is blue. So how can I represent this one? See, we know that whenever we have this kind of example, we can divide it into two parts. One is subject, another one is predicate. And what is the rule of representing this atomic sentence? That is, we can write blue means the predicate and then the subject. So this example can be represented like this. But here the question is it a WFF? So here my answer is yes. This representation is WFF. Now you can ask me this question. What is the rule? Means how I can ensure that it is a WFF. So here the rule is, I have already discussed, that is each atomic formula. So whenever we are dealing with any atomic formula, so you have to understand each atomic formula is a WFF. So what do you mean by atomic formula? Say I have another example. Say X is round. So I will write subject and predicate. So I will write round X. So why I am using this syntax? Because this statement is an atomic formula. So whenever we have any atomic formula, straight away we can say that it is a WFF. So this is the second example. Now, there is one important discussion about WFF. Now, pay attention to this example. According to WFF, there is another rule. So, apart from that three rules, we have another rule for identifying WFF. That is, say, if X is a variable, variable means we know that it will represent some object from the universe of discourse. And say A is a WFF. Then we can say that there exists XA is a WFF and all XA is also WFF. So this is the rule. Now I have to explain this rule. So what is the meaning of this rule? So this is the definition of the rule. Now I am going to give you one example so that you could understand what is the meaning of this rule. Say there is one statement given as X is blue, right? And there is another statement which is given as, say, X is round. Now if I ask you this question, that is, we have two atomic formulas, so they are WFF or not? So answer is yes. Any atomic formula is WFF. Now how can I represent this one? That is blue X and round X. Right. So now here if I write this thing, that is all X, blue X, round X. So here the question is it a WFF? My answer is yes, because we know this rule. So whenever we have some variable X and we have some representation, means WFF representation like blue X, it is itself is a WFF. Why? Because it is an atomic formula. Round X, it is itself a WFF because it is an atomic formula. So whenever we have variable associated with quantifiers and we have two or more WFFs together, it is also a WFF. Similarly, if I write all X, so I am using existential quantifier with some variable which is representing some object in the universe of discuss, and if I write it as blue X, which is a WFF since it is an atomic formula, and round X, then the entire representation will be considered as WFF. So this is the meaning of this rule. So now I am giving you one example so that we can discuss the conclusion. So what is that? So if I write taller within bracket, say I'm just writing A B, means what is the meaning of this representation? A is taller than B, right? So here the question is it a WFF? So my answer will be yes. But why yes? See, this statement can be written as A is taller than B. So it is dealing with constants, means it is a specific proposition. Also, it is a atomic formula. So it is a specific proposition as well as it is a atomic formula. Therefore, we can conclude that it is a WFF. So we are putting two rules together. Now, say I'm just writing this thing, that is, say taller A B, means A is taller than B, and taller say B C, means B is taller than C. So here my question is it a WFF? See, my answer will be yes, because we have discussed whenever two WFFs are connected via some connectives and enclosed within a parenthesis, then it is also a WFF. Taller A comma B is a WFF. This is the connective, and taller B comma C is also a WFF, and they are enclosed with a round parenthesis. So the entire representation is considered as WFF, right? And if I write this statement like this, say if X is a variable, say it is representing people in the world, then if I write taller X comma, say a person name, I'm just writing Ravi, or if I write for all X taller X comma Ravi, or I can write it as there exists X taller X comma Ravi. So here my question is, all these representations are WFF or not? Yes. See, taller X comma Ravi. So whenever we are using any variable which represents object in the world, that is here X is representing people in the world, and this representation is an atomic representation, atomic formula representation, so it is a WFF. Then According to this rule, for all x taller x comma Ravi, it is also a WFF, and similarly it is also a WFF using this rule. So this is how we can identify which one is WFF and which one is not. Now I am giving you another example. See, I am writing this thing. Taller, there exists x Ravi. Here my question is it a WFF? Then straight away your answer will be no, it is not a WFF. Why? Because I never discussed about this kind of rule. According to the syntactical rule representation, there exists x will be outside the fact representation like this. Since this syntax is not approved as a WFF rule, so it is not a WFF. Then similarly, if I write taller, say Ravi and say Ram and say Rima. Say if this is the representation, is it a WFF? My answer is no, because we haven't considered any of the representation as a part of WFF rules. Means inside a fact representation, we never allow any connective, or we never allow this kind of representation where two constants are connected via connectives and one constant is separated by comma. So it is not an example of WFF. Therefore, this representation and this representation is not a WFF. Say, let's consider one example. That is, Marcus is a man. I'm just writing some of the examples together. Two, Marcus is taller than Mauve. And the third one is every man drinks coffee. Now let's start with the first example. So is it a WFF? Yes. Since it is an atomic sentence, we can say that it is a WFF. So we can write it as man Marcus. So this kind of syntax are acceptable. Now this one, Marcus is taller than Mauve. Is it a WFF? So first question is it an atomic sentence? Atomic sentence means there we are not using any connectives. So is it a WFF? Marcus is taller than Mauve. Now try to recall a rule in WFF where we have the concept of constants. Remember, capital of India is Delhi. So whenever in a sentence we are dealing with constants, that is taller Marcus than Mauve. So these are the constants. So we are dealing with constants. So whenever we are dealing with constant, so it is a part of WFF, because according to rule number 1, any capital letter itself is a WFF. So here names, these names are considered as constants. So whenever we have constants and we can represent it like this, fact representation, taller Marcus Mauve, so it is a WFF, right? Now, is it a WFF? Every man drinks coffee. How you can represent this concept every? Do we need any quantifier? Then we have to use here what? Variable, right? So according to WFF rule number 5, what we have discussed, whenever we are using any variable which is representing something from the universe. So X is representing what? X is representing man, all man in the world. So whenever we have any variable X which is representing something, that is man from the world, all man from the world, and then drinks coffee, how can we represent? Man X for all we have implementation sign, and then drinks coffee. Who drinks coffee? X drinks coffee. So here my point is it a WFF? What is your explanation? Man X, this part, is it a WFF? X is a man. Fine. Now, drinks. X drinks coffee. Is it a WFF? So we have already discussed whenever we have two WFFs connected via connectives like this. So here implication is a connective. So this is a WFF, this is a WFF. They are connected via connectives, right? So it is satisfying one rule. Then we have already considered another rule whenever we have some variable along with this WFF representation, it is also known as WFF. So the entire representation is known as WFF. So what is the conclusion? So here the conclusion is it may happen in some representation two or more rules are applied simultaneously. Right? Here we have applied two rules or three rules. See, it is an atomic formula. This is the first rule. Then when two WFFs are connected together via connective, this is another rule. And for all X and then this representation, this is another rule. So we are combining many rules. So finally, what is the definition of WFF? So the definition is whatever rules we have discussed so far about WFF, whenever these rules are applied recursively on some sentence, then it is known as WFF. So whatever rule we have studied so far, whenever you are continuously applying those rules on a particular sentence, if you are able to do that, then it is known as WFF. So this is the definition of WFF. Now I have the last example. That is, say today is not Monday. Say this is the representation. So how we can represent this thing? So if I assume that P means today is Monday, then today is not Monday. How can I represent? Not P. Right? Now my question is, not P is WFF or not? Whenever any proposition is prefixed with not, then it is a WFF. So yes, answer is it is a WFF. So it is also in a rule, right? So this representation, you can write it as P is today is Monday. You can use capital P also. So today is not Monday means not P. So we have already discussed prefix not. Not is a prefix for P. So therefore, this representation is WFF. So if I write this kind of representation, this one and this one. These two examples are WFF or not. So here the question must be like this. We are assuming that A and B are WFFs. See, whenever this question is asked, this line must be mentioned beforehand. If A and B are already defined as WFF, then any two WFFs which are connected via connectives. So in the list of connectives, we have these symbols also. So whenever we have this kinds of connective between two WFFs which is enclosed with parenthesis, then it is also known as WFF. So yes, these two representations are in WFF. So this is all about WFF.